Hello, Algebra 2 class. How are you doing? Thank you for your comments and suggestions and let me know the problems you had with our first lesson. I think overall it went pretty well. I think you guys did a great job. I'll get better. Needed to improve, but that's my goal. So today we're doing the second section of the chapter about radical functions. And we're not talking about radicals just yet. We're getting there. You're going to see a progression. Today we're talking about inverse functions and relations. Remember the difference between functions and relations? If not, I'll remind you later. So that's our objectives. We're going to find the inverses of a function or a relation, and we're going to determine whether two functions are inverses of each other. I'll show you a couple ways to do that. And over here, of course, is the practice problems I want you to do. And again, I know some of them are even problems, and I'll provide you the answers to all those. And hopefully get them right. Okay. So what is an inverse? You can read right there. An inverse is the switching of values of a coordinate pair. You just switch the numbers around. So it seems kind of odd when you think about that's all we're doing. All we're doing is taking these numbers. We're taking that 1, 5 and just making it 5, 1. Yes. Now, you're skeptics, as you should be. 7, 12, my birthday becomes 12, 7. So you're skeptics and you're going to say it can't stay that easy. Well, of course not. We're going to study some things about inverses and you're going to see how it affects the radical functions we'll be talking about in our next lesson. Notice 4, 4 stays 4, 4, obviously. Which means 3, 3 would stay 3, 3, 2, 2, 1, 1, 0, 0, negative 5, all those numbers. Is that significant? We'll find out. So here's an example taking you back to your days of geometry. Remember when you would graph functions and then do things to them? Transformations, they were called. So what we're going to do is we're going to graph this triangle. There's 1, 1, 3, 5. And I said triangle just because I know it has 3 points, and I know those points are not collinear because I've already tried it. So there's our triangle. Okay, let's draw that triangle. And just so you know, I'm working on my lines. My lines aren't perfect yet. I mean, they should be perfect, but as soon as I let go of this little pen, sometimes they slide off a little bit. So my plan is to get better with this as we go along. But anyway, there's my triangle. So there's A, and there's B, and there's C. Now you wondered why I wrote A in there? Well, planning ahead because you're going to see what happens. So let's take this, and now let's do the inverse of those points. So we're going to create a new point A, which is still 1, 1. A new point B, which will be 5, 3. And a new point C, which will be 4, negative 2. And let's graph those. 1, 1, as expected, is the same point. 5, 3 will be up here. The new B, as we say. And 4, negative 2 down here, the new C. And the new A is right here. All right, now let's make this triangle and see what we've got. There's that one. There's that one. And there's that one. So what are those two triangles' relationship? What does it look like? Now, do you remember from last year what you used to call those things? You may not, but I will remind you. Those are reflections. Now, what does it reflect across? It's not the y-axis or the x-axis, but it looks like this line. Could it be? Is this? So if I folded those two images right along that line, would they match up? And they would. And you know what this line is? This is the line y equals x. This is where it's negative 5, negative 5, negative 4, negative 4, negative 3, and so on up to infinity. So that's the line of symmetry for the reflection of a graph and its inverse. It's going to be the same in algebra. we're going to take some graphs and we're going to show their inverses on the graph. So to make this answer a little more correct, remember we used to write a reflection over the line y equals x. Let's put it into a little algebraic equation. What's the inverse of that function, and then what's the graph look like? So let's look at the original function first, y equals 4. Well, do you remember what y equals 4 looks like? Yeah, that's an interesting color. Let's try that one. That's y equals 4. Okay. So if that's y equals 4, what's its inverse? Now let's think about it this way. Let's set this one up kind of as a table. So if you have an x and a y, okay, any x value you pick, what's the y value going to be? 4. If I pick 2, the y value is going to be 4. If I pick 28, the y value is going to be 28. Ah, wrong. It's going to be 4. So anything I pick will be 4. So would you agree that 0, 4, 2, 4, and 3, 4 are all part of that line? Remember, when we say inverses, we're switching the x's and the y's. If I want to find its inverse, I am going to switch the x's and the y's. So it's going to be 4, 0. It's going to be 4, 2. It's going to be 4, 3. Notice I still kept this x and this is y because this is my new input. 4 becomes 0. 4 becomes 2. 4 becomes 3. So what happens there? Well, I get myself a new line. And that line is this one. You know what that line is? That line right there is the line of x equals 4. Does that line reflect across there? It does. This is the equation, and that's the graph. Okay? Again, starting out nice, and we'll throw a little bit more complicated measurements into it. So the inverse of each function, 3x. I'm going to show you a way of rewriting that equation. Now I just put y in place of f of x. They really mean the same thing. This is f of x, which is the y-axis. Here is how you can actually find the inverse of a function with this one little trick. You switch the x's and the y's. Yes, just like you did there, you switch the x's and the y's, you do the same thing here. But when we ever graph an equation, don't we usually solve it for y? Okay, so if I solved it for y, what would I get? I'm going to divide both sides by 3. And I'm sorry, I didn't mean to put that over there. So this would be x over 3 equals y, or the way I like to write it personally. This is the way I like it. Y equals 1/3 x. So let's graph y equals 1/3 x. Again, you can make a chart anytime you want. You can do an XY chart and fill out graphs, or fill out the tables and graph the points. That's fine. I don't care. You could also do it with the slope-intercept form. Y equals mx plus b. What's the b value? 0. Crosses right through here. What's the slope? 1 up, 3 right. 1 up, 3 right. Which also works in reverse. 1 down, 3 left. Wrong color, but you know what? We're okay for now. We'll just deal with that. Okay, so there's my graph of y equals 1/3 x, which is my inverse. Now my original equation was 3x. And how do you graph 3x? Well, same way. We'll start at 0, because remember it's y equals mx plus b. The y-intercept is 0. But now my slope is 3, which means I go up 3 and over 1. Or down 3 and 1 to the left would be the same thing. Now, how do we know that this graph is correct? Well, besides the fact that absolutely know we did the math correct. But look at its shape. Is that shape what we would expect? Is it flipped over this line? This is the distance between here and here the same as the distance between here and here. Sorry, I used the word here. Between the function and the line y equals x, same distance as the inverse to the line y equals x. And all these things too. It takes 2 horizontals to get to this one. So it should take 2 verticals to get to this one. Okay? Any way you want to think about it, that's an inverse. Okay? But just so you know, that is right there the inverse of that function. Let's try this one. Let's find the inverse. I'm going to change that f of x to y again. Switch them. Solve for y, because we're used to solving for y. So what I'll do is I'll add 1 to both sides, and then divide by 2. And then I'm going to write it like this. Alright. Here's the inverse. Let's graph it. You know, in this case, I think I want to make a table. I think it's a little bit more straightforward than finding the y-intercept, which would be 1/2, and the slope of 1/2. So give me, that's a line. We usually pick 3, right? Because 2 make a line, but the third one confirms it. So give me an x value. Start with an easy one. You know what? 0 in this case, would it be an easy one? Because what is 0 plus 1 is 1, and 1 divided by 2 is 1/2. Now, could you graph 0, 1/2? Sure you could, but me personally, I like to stay right on the grid. So I'm going to pick an odd number like 1. 1 plus 1 is 2. 2 divided by 2 is 1. Interesting, the point 1, 1. I wonder if its inverse will have the same point. Pick 3. 3 plus 1 is 4. 4 divided by 2 is 2. 1, 2, 3, 2. And that looks like it's good. We'll do one more that didn't have a fraction. So I'm going to do 5. I'm going to do the negatives. I will do 5. 5 plus 1 is 6. 6 divided by 2 is 3. And that follows the right slope. See, up 1 over 2, up 1 over 2. Okay. So our graph of our inverse is this. Okay. So our original function looked like. Remember, our original function is going to be a reflection across this line. Okay, we know 1, 1 is going to be on it. I'll tell you what, here's a little trick. Since we have this table up, let's just use this table. If we have 3, we get 5. Remember? 5, 3, flip them. 3, 5. 2, 3, 1, 1. Graph it. What do you see? Alright, does that look good? Does that look like an inverse? It's not perfect, is it? I don't think that line was perfect. That's close enough. See the inverse? It's not close enough. It's driving me crazy. That's better. Okay. See the inverse? That's how you do it. And if you notice, that red line is 2x minus 1. The y-intercept is negative 1. Slope is 2. Go up 2 over 1, up 2 over 1, up 2 over 1. So however you want to graph them, remember, use a table. Use your knowledge of slope and y-intercept. Totally up to you. But that's how you graph those functions.